Hello and welcome to the CloudOps Summit 2021. We are Kubermatic and we are a cloud-native company that writes and distributes software all around Kubernetes and cloud-native initiatives. Today we have three topics that we would want to discuss, and I am really pleased that my fellow developer colleagues are here today to present you some pieces about Kubernetes operators and a piece about monitoring, logging, and alerting, and how to set up Kubernetes everywhere. And I think without further ado, I'd like to introduce Jiacheng Shao, who is one of our developers for the KubeCarrier project, and he will talk about Kubernetes operators.
Hi everyone, my name is Jiacheng Su, and I am a software engineer at Kubermatic. Today I will talk about why to write operators for Kubernetes. So what are Kubernetes operators? Operators are software extensions to Kubernetes that make use of customer resources to manage your applications and their components. Operators can bring us many benefits. It automates operational tasks for you, for example, deployments, upgrades, backups, which are normally supposed to be done by human operators. And it makes your applications more Kubernetes native. You get lots of built-in features of Kubernetes out of the box. You can interact with your applications with Kubernetes APIs and kubectl toolings. It also provides a possibility to test your application operations and takes the error-prone human factor out of your application lifecycle management. Last but not least, the application management in multi and hybrid cloud will benefit the great capability of operators because operators can work with different Kubernetes distributions. A Kubernetes operator can be namespace scoped or cluster scoped. A namespace scope operator watches and manages resources in a single namespace, and a cluster scoped operator watches and manages resources in the whole cluster. Namespace scoped operator provides the flexibility to run different versions of an operator independently in a cluster, which may be helpful, for example, in case of dev environments or in single cluster environments. On the other side, the cluster scoped operators work better in managed and highly distributed environments. As only one instance of the operator needs to be run in each Kubernetes cluster, it is much easier to manage across many clusters and can save huge amounts of resources in case of many tenants. At Kubermatic, we provide a central service hub with power of KubeCarrier project and cluster scoped Kubernetes operators. KubeCarrier provides multi-tenancy support by leverage resource escalations by Kubernetes namespace, and the cluster scoped operators can manage service instances across multiple namespaces, which reduces the maintenance burden and the complexities of service management across multiple clusters, clouds, and regions. That's it from my side. Thank you for your attention.
Then thanks a lot, Jiacheng, for this short introduction into operators. If you want to know more, reach out to us. Jiacheng will provide some expert assistance with your questions. And now it's up for Rastislav to talk about implementing a monitoring, logging, and alerting stack for a highly distributed platform.
Hello, so my name is Rastislav Sabo, and today I'll be speaking about implementing monitoring, logging, and alerting stack for a highly distributed platform. So a typical monitoring, logging, and alerting stack in a Kubernetes cluster may look like this. We'll deploy several different components into the Kubernetes cluster, such as Prometheus for scraping the application metrics, Loki for doing that for the application logs, Grafana for providing the user interface to access the logs and metrics and the dashboards generated from them. And maybe Thanos and some cluster storage for providing long-term storage of our metrics and logs. So in case of 2 Kubernetes clusters, we would usually repeat the process twice and have all these components running in each cluster. But in case of many Kubernetes clusters, this approach becomes really hard to manage. We would need to install and set up the same components too many times. And in case of version upgrades, we would need to do that across all clusters, which is really hard to manage. So how can we solve this with the Kubermatic Kubernetes Platform? Since Kubermatic Kubernetes Platform has a hierarchical architecture in which the control plane components for multiple user clusters run in a single seed cluster, we can build our MLA stack on top of this hierarchy. So in the user clusters, we would deploy just the stateless components that would stream the metrics and logs to the seed cluster. And in the seed cluster, we would deploy all the complex components that are responsible for long-term storage and user interface that respects the multi-tenancy, so that every user can access only data for those clusters they have access to. In an even more distributed environment, where we would have multiple seed clusters located at different locations, we would use a similar approach. So the user clusters would contain just the exporter applications, and the seed clusters would store all the data. But as you can see, the data is still located closely to the user clusters. So in the same location, we don't want to stream all those data across the locations. At the same time, we can provide a single Grafana user interface in the master cluster that would allow us to access the logs and metrics across all the clusters in this hierarchy. So to summarize, the Kubermatic Kubernetes Platform monitoring, logging, and alerting stack provides the following benefits. Easy installation in the user clusters with a single click or an API flag, or even it can be installed by default into every cluster. Easy data operations and upgrades of the components in the user clusters because they are tiny and stateless. Low footprint for the user clusters, which is especially important for the edge use cases where we run our worker nodes often on resource-constrained nodes. Single pane of glass for even thousands of clusters through which we can access all the logs and metrics across all clusters. And the multi-tenancy support so that authentication and authorization is integrated with KKP, users, projects, and roles, which provides us either per tenant Grafana view for logs and metrics, or a global admin Grafana view for logs and metrics and alerts. Okay, that's it from my side. Thank you for your attention.
And thanks a lot, Rastislav, for this very interesting overview how to observe a multitude of clusters in parallel. Coming to our next speaker would be Marco, who's going to talk about how to write software that sets up Kubernetes everywhere. He is one of our contributors to the Kube1 project. So go ahead.
Hey everyone, I am Marko Mudrinic. I'm a software engineer at Kubermatic, and today I'm going to talk about how to write software that sets up Kubernetes anywhere. This is a story of what we learned while creating a Kubernetes cluster lifecycle management tool called Kube1. Installing Kubernetes doesn't have to be hard. Kubernetes is a complex system, but we are going to see how we can use existing tools to make this task easier. Let's start with a 10,000 feet view of how should the cluster management tool look like. First, we have a user-provided manifest that defines how should our cluster look like. The manifest is given to the tool, which creates a new cluster based on the provided manifest. This way, we implement a declarative approach, which brings many advantages and is widely used in the Kubernetes ecosystem. The question is, What should our tool do? The Kubernetes community is large, and it created many tools to make managing clusters easier. You should always reuse as many tools as possible, instead of implementing everything from scratch. I want to highlight KubeADM. It is official Kubernetes cluster management tool that creates production-ready, conformed clusters out of the box. KubeADM does everything Kubernetes. It provisions the control plane, the working nodes, it can upgrade the cluster, manage configuration, certificates, and more. And the mostly important, it works anywhere, on cloud, on premises, bare metal, and more. However, the KubeADM's philosophy is that it only takes care of Kubernetes and Kubernetes cluster management. It is supposed to be used as a building block in other tools and scripts. What about everything non-Kubernetes? For example, infrastructure and provisioning instances, configuring instances, installing packages like container runtime, kubeadm, kubelet, running kubeadm itself, and installing add-ons like CNI, metric server, and everything else needed. For configuring instances, installing packages, and running kubeadm, we can use well-established tools and protocols like Cloud Init or SSH. For installing add-ons, we can use kubectl, ClientGo, Helm, or whatever else works best for you. However, what about the infrastructure and provisioning instances? This is potentially the hardest problem to solve. There are way too many providers and setups, like cloud with AWS, GCP, and much more providers, on-premises with vSphere and OpenStack, and bare metal, Edge, and so on. And every provider is different. Every provider has different features, different structures, and APIs. And there are also endless possibilities of terms of architecture, which makes the problem even harder to solve. I will highlight the 3 common approaches to solving the infrastructure problem. The first one is to implement infrastructure management in our tool. The second one is to use external infrastructure management tool, for example, Terraform. And the third one is a hybrid approach, a combination of previous 2 approaches. Managing the infrastructure ourselves looks something like we have seen before. This time, the manifest will include the information about how the infrastructure should be created, along with the information about the Kubernetes cluster. The tool will create the infrastructure and instances, and then install and provision Kubernetes on those instances. The problem with this approach is that we lose ability to create clusters anywhere. If our tools doesn't support some provider or architecture, user will not be able to use it, unless we don't extend the tool. To solve this problem, we can use an external infrastructure management tool, such as Terraform. We'll use it to create the infrastructure and provision instances, and then we are going to provide the information about those instances and how to access them to our tool. The user-provided manifest will only contain information about the desired Kubernetes cluster. The tool then could use SSH to access instances and install Kubernetes there. Finally, the hybrid approach assumes combining the previous 2 approaches. We have decided to go with this approach with Kube1 because it offers a lot of flexibility. The external tool is used to create the infrastructure and control plane instances, and then our tool would provision and manage the Kubernetes control plane. Then we implement a cluster API-based Kubernetes controller that is used for managing working nodes. That way, we can manage our working nodes using the Kubernetes API and use features such as autoscaling and more. That's it for today. Thank you for your attention.
Thanks a lot, Marco. So this was our little short and rough tour through everything Kubernetes and Kubermatic does, far and in between. If you want to reach out, feel free to send us an email, to contact us via social media. And we were glad that you took your time listening to our topics and I hope we'll see each other soon.